Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture of this course on robust control. So in the previous lecture we have introduced one of the most important, purportedly one of the most important factorizations that you are likely to encounter while doing any course on, say, matrix theory, which is known as the singular value decomposition. Now the reason that this is very important is that this does not distinguish between whether the matrix is square or rectangular, wide, that is fat, or tall. Right? So that irrespective of the number of rows and columns of the matrix, every single matrix always has a singular value decomposition. Right? So that is one of the most pivotal results, and it will turn out, as we shall see during the course of this lecture, that from the singular value decomposition of a matrix, a lot of these subspaces associated with the matrix begin to make sense in the sense that you begin to see the basis for these subspaces carefully preserved in this singular value decomposition. It becomes very apparent, it becomes very explicit. Not just that, the fact that these bases also turn out to be orthonormal, right? That is another beautiful aspect of the singular value decomposition. So to refresh your memory, we ended the last lecture with just describing what a singular value decomposition for a matrix looks like. We considered a matrix, say A, right, which is a complex matrix of size m cross n. We are not imposing any restriction for the time being on m being greater than n or less than m whatsoever, right. And then we say that let there be this integer p, which is the minimum or the lower of the two numbers m and n. Then you can write such a matrix A in the form U times sigma times V Hermitian, where U is an m cross m complex matrix which is also unitary, V is an n cross n complex matrix which is also unitary, and the sigma, it's like a pseudo diagonal matrix. It's m cross n, so not really a proper diagonal matrix, right, but it's off diagonal entries. That is, if the column index and the row index of an entry are not equal, then that particular entry must be 0. On the other hand, if the column index and the row index of a particular entry happen to be equal, then they must be positive semi-definite. Yeah, that's all that we are saying. Okay, and these numbers that sit at these diagonals or these pseudo diagonal entries of this sigma matrix, they are what we call as the singular values of A. Now, as has been the case so often with this course, we will not really talk about it in terms of a formal theorem lemma proof kind of a structure, but rather we will go about just proving and convincing you that this singular value decomposition must exist for every matrix, whether it's tall or fat or wide, right. So why should it be so? So let's start with an arbitrary matrix. I wouldn't like to call it a proof, so let me just draw a line below the statement of that result, and subsequently now we shall try to convince you that indeed every matrix does have a, every complex matrix does have a singular value decomposition, right. Okay. Now consider the matrix A Hermitian times A, okay. Irrespective of what A is, whether A is Hermitian or not, A is square or rectangular, whatever it is, I know that this matrix A Hermitian A is always going to be Hermitian, right. This is, yeah, n. So suppose A comes from m cross n. Then of course, the size of A Hermitian A is n cross n. Not just that, because of this property, we say that it belongs to Hn. And we have just seen in the previous lecture some beautiful properties of matrices that are Hermitian, right, that they can always be diagonalized, right, where those matrices that indeed do turn out to diagonalize this particular Hermitian matrix are also unitary themselves. And in other words, what we have seen is that any Hermitian matrix has orthogonal or even orthonormal eigenvectors, a set of eigenvectors which span the entire space, and they are also an orthonormal basis for the entire vector space, right. That is what we have seen about Hermitian matrices. We have already proved that, at least convinced you that it is true, right. So, now that we have this matrix A Hermitian A, we have now shown you that this is also indeed of that same class of matrices, that is Hermitian matrices, and therefore, this A Hermitian A must be diagonalizable by a unitary matrix. Okay. So, let us say that this A Hermitian A is indeed diagonalizable, and so we say that A Hermitian A can be written as V sigma V Hermitian. Okay. Of course, you could have written V Hermitian sigma V, it really would not matter much, where well, let me just sort of clarify this a bit. When I write this as a sigma, I should probably make a distinction here, where I say that this is sigma hat, and this is a 0 block, this is also a 0 block, and this is also a 0 block, right, where of course you can have 0 eigenvalues as well of A Hermitian A, right, but at least there are R. So, this is an R cross R block. So, there are at least R non-zero eigenvectors, right, yeah. If all eigenvectors are 0, well then bad luck, right, then it is just a 0 diagonal matrix, but if not, then at least R of the n, rather R of the n, because you see this is H of n, right. So, this is an n cross n matrix A Hermitian A. So, it has n eigenvalues, out of which R we are claiming are non-zero eigenvalues. Okay. In other words, we are saying that the rank of A Hermitian A is going to be R. Okay. Try to correlate these results. We have already spoken about how rank is related with non-zero eigenvalues of a square matrix, right. We have shown you already that if there are a certain number of non-zero eigenvalues of a square matrix, then that is also the rank of that Hermitian matrix, okay, not just square, let us say Hermitian matrix, right. We have already shown you about those results. Okay. So, if this is so, then we have this sigma hat. Let us just clarify this. This is just because you know the eigenvalues are also going to be real. So, this is R cross R in size. Okay. No problems so far. What we have used so far is nothing but known results. Once we have seen that A Hermitian A is a Hermitian matrix, right, then we can immediately say that it is diagonalizable unitarily, where of course, and V star V is equal to V V star is equal to identity of size n cross n, right. So, it is unitarily diagonalizable by virtue of being a Hermitian matrix, nothing out of the ordinary thus far. In addition, because these entries in sigma hat are all real numbers, it makes sense to have an ordering, yeah. So, suppose in addition we say that sigma hat's ith entry, yeah, is greater than equal to sigma hat's jth entry if I happens to be greater than j, okay, right. So, we are saying that there is an ordering. So, the first entry of the diagonal of sigma hat will be the largest, the next one will be lesser than or equal to that entry, the next diagonal entry will be lesser than or equal to that. So, there is an ordering until of course, you come up with all 0 diagonal entries at some point if r is less than n, right. If the small r is less than n, then eventually you will end up with a line of zeros sitting in the diagonals, right. But before that, not just this sigma hat, not just that the sigma hat has any arbitrary structure, but also there is an ordering among the diagonal entries of this matrix, right. So, of course, I have probably missed out there, and so let me mention that I have mentioned it in words, but let me write that down. That sigma hat is a diagonal matrix. Needless to say, I am not writing this here, but those diagonals are precisely the eigenvalues of A Hermitian A, right. So far, we are doing okay with this, right. There is absolutely no issues with whatever we have done so far. It is quite clean and clear, right, crystal clear what we have done here. So, if you want to assure yourself that this is going to be, these diagonal entries are going to be positive, yeah. So, again I am not writing all of this down, I will discuss this. Why do you think this is positive? Because if this is a positive semi-definite matrix, then we can say that. Now, why should A Hermitian A be positive semi-definite? Well, I am putting it to you that it is pretty obvious. You hit A Hermitian A with an X Hermitian on the left and an X on the right, right. Then what do you have? You basically have the square of A Hermitian X norm. What I am saying is, okay, let me not be so miserly with writing. So, check that for x not equal to 0, so x obviously belongs to n cross 1 or just n, right. We have x conjugate A Hermitian A x can be written as A x whole Hermitian times A x, yeah, which is nothing but A x the norm squared, yeah, which is greater than or equal to 0. Why am I not discounting the fact that it can be equal to 0? Because of course, if you happen to choose an x whose last n minus r tuples are non-zero, but the first r tuples are 0, then you can end up with a situation where even though x is not equal to 0 itself, yeah, it is not the n tuple of zeros, yeah, yet you can have that Ax is 0, right. But at best it can be 0 or positive, but never negative, right. So, because that is so, therefore, this A Hermitian A is positive semi-definite. At worst it is positive semi-definite, at best it is positive definite. So, if it is positive semi-definite, then its eigenvalues had better be non-negative as well, and therefore, when these eigenvalues which are sitting in an ordered fashion in this sigma hat, yeah, following this ordering, yeah, I can always write or arrange these eigenvalues in that particular order, because these are after all just some positive real numbers, okay. If they are equal, then it does not matter which order I am putting them in. So, 2 and 2, which 2 I am putting before the other 2 is it is immaterial, right. 5.1 and 5.1, yeah, they will only be distinguished by the eigenvector, and there too it does not really matter, yeah. So, only when there is a perfect ordering, it is 5.1 and 5.12, then 5.12 will sit on the row and column ahead before, and 5.1 will sit on the row or column below it, right. That is the ordering, okay. So far at least we know how we are proceeding, and nothing fancy has been done, or no special tricks have been played yet with this, right. So, then what can we do about, what can we say about this? Here is where we make the first choice. Suppose I choose a matrix J, yeah, in this fashion. What is this J going to be? Now, notice that this original matrix has zeros sitting here, right. So, I choose this J matrix now to be very similar to this original matrix, except for the fact that I retain the sigma hat from the original matrix that was present here, right. In addition, Whatever was a 0 here, I replace it with a suitable identity matrix of size n minus r, right. That is the only change I do. And why am I doing this? Because now notice what I am going to do. Consider the matrix J inverse V Hermitian and then A Hermitian A times V times J inverse. What is this going to look like? Now look, this A Hermitian A, we have already seen that it looks something like this, yeah. So let me just substitute this in place of A Hermitian A. That is going to look like J inverse. This V is, by the way, that same V which appeared as the this V star is basically the the eigenvector set, no, yeah. So this V is basically the columns of this V are basically the eigenvectors, right, yeah. So because if I post multiply this, that is right. So the columns of V are the eigenvectors of A Hermitian A. So that is the V. So that same V I have now chosen here, okay. So this is going to be nothing but V, then that same sigma hat 0 0 0 V Hermitian and V, and then followed by another J inverse. Now I am going to get rid of these brackets and allow these fellows to pulverize each other. So this leads to an identity of size n, this leads to another identity of size n here. So what I am left with then is this J inverse times this sigma hat 0 0 0 and this J inverse. Okay, I think I have missed something here. Okay, yeah. I think what I missed here is that this in the definition of this J here, in the definition of this J here, I should have been a little careful. So I should have called this the square root, okay. Apologies for that mistake, So I should have called this the square root, the positive square root. So you might wonder what this square root of the sigma matrix means. Of course, you know that this sigma matrix looks like a diagonal matrix of size r cross r, where all its diagonal entries are positive. So when I am saying it's a square root, it is basically the square root of the individual diagonal entries. It is just like the idea of square root of numbers, real numbers, positive real numbers. You multiply a number with itself and you get a square, right, square of that number. So you now multiply this matrix, this particular matrix, each of whose entries is basically, each of whose diagonal entries is basically the square root of the corresponding matrix here, So now if I am allowed to do this, then I can write this as, you see, the square root of sigma hat inverse 0 0 I, because obviously we know that the inverse of a diagonal matrix is taking the inverse of the individual diagonal entries, and this is sigma hat, this is 0, this is 0, this is 0, and again this is square root of this sigma hat 0 0 0, this is inverse. So now notice what we are going to get is nothing but, if you take block wise, these are 2 by 2 blocks. So if you take the multiplication in that block wise sense here, what you are going to get is sigma hat square root times sigma hat, so sigma hat square root inverse, times sigma hat square root inverse and then 0 0 0. Now what will this result in? Think of a diagonal matrix and its square root multiplying it ahead and behind it. It is just going to be the identity, right. So it is just going to lead to this identity R 0 0 and 0. Now notice, what did we start with? We started with this expression. Can I not write this expression also in the following form? So this expression is also nothing but J inverse V star A star, I am just using the associativity of matrix multiplication, A V J inverse, which is in turn equal to, now if you take the whole matrices Hermitian operation, and J inverse is obviously a diagonal matrix, so whether you take its Hermitian, a real diagonal matrix, so whether you take its Hermitian or not really matters not. So this is basically then just check and convince yourself that I am not just glossing over this, so you have to actively work with me on this. This is nothing but A V J inverse. So on one hand, this red part that I have worked out tells me that this is nothing but equal to this, and on the other hand I have worked it out here and I have realized that it is going to be nothing but this. So piecing together these two things, what I might then conclude is that this AVJ inverse conjugate, AVJ inverse conjugate or Hermitian times AVJ inverse is going to be equal to IR 0 0 0, right. Now let this matrix be given a name, say this is a Y matrix. So this is Y Hermitian and this is Y. Then what can we say about this matrix Y? First of all, what is the size of this matrix? This is M cross N, this is N cross N, and this is N cross N, right. So this belongs to C M cross N, right. So this whole thing is now N cross N, right. So on the right hand side we have this N cross N, and on the left hand side also we have N cross N. But what does this tell us? This tells us that if I now write this fellow, look at the size of Y. So this is Y, okay, let me just write it down elaborately. So if Y is an M cross N matrix, then Y can be written in the following fashion. I can write this as Y1, Y2 dot 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 till it will have N columns, right. Yeah, where of course this yi, each of them are m tuples of complex numbers, and there are n such m tuples, right. So what does this tell me then? This tells me that this above relation then translates to y1 Hermitian, which is a row, y2 Hermitian, which is another row like this, till yn Hermitian, which is a row like this, times y1, y2 dot 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 till yn. Yeah. So this is nothing but equal to y1 Hermitian y1, y1 Hermitian y2, likewise till y1 Hermitian yn. Similarly, y2 Hermitian y1, y2 Hermitian y2 dot 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 till y2 Hermitian yn. Right. Last one is yn Hermitian y1, yn Hermitian y2 dot 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 till yn Hermitian yn. Yeah. So this is while proceeding from the left hand side, but while proceeding from the right hand side, what do I have? This matrix has to be also equal to, then from the right hand side has to be equal to 1 1 1 1 like this, till this is an R by R block, R by R block of all ones, yeah, and these are all zeros. So this is n minus R, this is R, this is n minus R, right. So all these sizes are now accounted for, right. Yeah. So now what does this tell me? If I now compare the entries from here and the entries from here, what can I say? I know then that this set of vectors that constitute this matrix Y as the columns of this big matrix big Y, yeah, they must be orthonormal. At least the first R of them. That is what this identity matrix is telling me, at least the first R of them. Therefore, y1, y2 dot 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 till yr must be an orthonormal set of vectors, because when you take their inner products with themselves it leads to unity, and you take their inner products with any other fellow by comparing these entries, the cross terms here, they vanish. So, they are an orthonormal set. What about the last n minus r fellows of this fellow y, this vector y, the last n minus r? You see, compare the diagonal entries, they are all 0, and the diagonal entries are always giving you the norms of those vectors. So, if the norm of a vector is 0, then that vector also has to be 0, right. So, therefore, y r plus 1 is equal to y r plus 2 is equal to dot 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 till y r must be the 0 vector in, let me check the size, yeah, in Cm, right. So, this we can now deduce immediately from this, but what does that mean? What was originally my y? Y was nothing but A V J inverse, right. So, therefore, I can now deduce that A V J inverse, the way I have described V and the way I have defined J inverse and J, must be equal to this y, where we have y1, y2 till yr, and then all zeros, right, 0, 0, dot 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 till 0, right. So, the first r entries of this, the first r columns of this matrix A V J inverse are an orthonormal set of vectors, and the remainder are all zeros, right. So, this I can now say that is what this multiplication will result in. So, now can I not write that A is equal to this matrix, this first r columns of this y matrix that I have here, let me call that u hat, let me call this u hat, and what is the size of this u hat? This u hat has m rows and r columns, right. So, this u hat is an m cross r complex matrix. So, this is u hat and this is a 0 block. What is the size of the 0 block? Well, of course, this is of size again m cross n minus r, okay. Sorry, this is n minus r, or let me see. Of course, J is a square matrix, so I just want to make sure that I have not calculated incorrectly. Yeah, so V is n cross n, so J also has to be n cross n. Yeah, that is correct. So, if J is n cross n, yes, yes. So, this is n cross n. So, there are indeed m columns and m rows and n columns. So, this is m cross n minus r, yeah, no mistake there, right. Yeah, that should be okay. Yeah, it should be n minus r, yeah, okay. And of course, I have to post multiply. First, I have to hit it with a j on the right to get rid of this j inverse. So, first I take this j here on the right, yeah, and then I hit it with a v Hermitian on the right. If I hit it with a v Hermitian on the right, then I can get rid of this v as well. So, this is what A is going to look like for me, right. But what is this A going to be like? This is going to be like, this is going to be u hat 0, and remember the structure of this j, it was nothing but the square root of that sigma hat that I had defined, and the 0 and the 0 and the identity here, and then of course, I had the v hat. So, now what we are going to do is we are going to just replace this, we are going to say that, well, this we can further write as this u hat, let it remain here, and let us say we append this with a u tilde here, yeah, and let us say we call this a square root of sigma hat 0 0 0. Why are we replacing this? So, remember we are just saying that replace this with any arbitrary u hat here and replace this I with 0 here, sorry this not here, replace this I with a 0 here, right. Now, once we do this replacement here, in the overall scheme of things this will not make any difference. Why can we safely claim that this will not make any difference? Precisely because when you have a 0 here, this 0 multiplying with this I, when you do the second multiplication of this u hat with this and this 0 with this, it leads to 0. Now, on the other hand, if you replace this with a u hat here, it will not make any difference when you multiply with here the 0 here, but when you multiply this with here also, you will still lead to a 0. So, overall the result of these two multiplications here and the result of these two multiplications here are going to be the same. So, therefore, you still have that V star here, yeah. And now we say that this u tilde could be any arbitrary matrix, sub matrix thereof, right. So, why not just replace u tilde, or rather choose u tilde such that yeah, this is where we make this choice, choose u tilde such that u hat u tilde is an m cross m unitary matrix, yeah. So, remember here what did we have, yeah, here what we had was this size of this fellow was m, sorry this fellow was r, I am sorry, size of this fellow was r and m, right, and this fellow was n minus r. So, you had a n minus r columns of zeros. So, now instead of n minus r columns, you replace it with m minus r such columns, okay, such that it completes a basis for Cm. So, this is basically m minus r, and the remaining, so if n is greater than m, we are assuming here, again this is where we bring in the assumption, it will not really matter in the long run whether you choose n greater than m or m greater than n, yeah, because if A has a SVD, then A star also, A Hermitian also has an SVD. So, then we are replacing this with fewer of them, right, and this also you append here. So, the size is not the same, alright. So, for example, here you had an n cross n size, remember this J is n cross n size, no, but here we are saying that we only have replaced m of them here. So, this is basically of size m, right, whereas the number of columns of this still remains n, the columns of this overall matrix, this remains n. So, here is what the overall picture looks. So, originally you had u hat 0, this square root of sigma hat 0 0 I and V star. So, forget about the V star for the time being, we are just focusing on this first part of the product, yeah. What I am saying is that let us replace this without any loss in or change in the overall expression, let us replace this. So, what are the sizes of this? This is basically r columns, this is m rows, and this is n minus r columns, yeah, again m rows obviously. Here this is r cross r, yeah, and this, as it is coming from the J matrix, this is the J matrix. So, this is an size n minus r, n minus r, alright. Now, we are saying that we are going to replace this with u hat and u tilde, but remember this u tilde is no longer of size n minus r, but of size m minus r by my choice, because you see ultimately whether you have additional columns of zeros, when you multiply by them it adds nothing, it does not change anything, right. So, therefore, we can safely keep it as it is, retain this, this size is m minus r, and here also now I retain the first part of it, 0, 0 here. Now, instead of having n minus r additional rows here, this I am going to replace with a 0 matrix of size m minus r. So, remember this difference here, this is m, but this is n. Yeah. So, I am also reducing the size of this or changing the size of this. If m is greater than r, then I can actually increase the size. It really does not matter, because these are after all just concatenation of some 0 blocks or removal of some 0 blocks from the overall multiplication. Just convince yourself that this is not indeed so. This still however remains n minus r, and then you have the v star. So, I am saying that whether you do this operation or the former operation, it will not make any difference. In the end you get the same m cross n matrix, and this is what the SVD is, right. So, therefore, we have a unitary matrix U, another unitary matrix V Hermitian, and this matrix which is like sigma 1, sigma 2 dot 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 till sigma r, yeah, zeros, zeros and zeros, yeah. So, therefore, A can be written as a product of these 3 fellows, okay. This is what A is, and that is indeed the SVD, and that is what we set out to prove to you in the first place, right, that every matrix irrespective of the sizes of m and n will always have an SVD, right. So, we have hopefully been able to convince you that this is indeed the case, okay. Now, why is this SVD particularly important, and what other insights can we glean from this by looking at this SVD, okay. Now, think of this A matrix, okay. Consider any vector in Cn. What do we know about this matrix V? Let suppose x, okay. So, consider any vector in Cn, say x. Let x is equal to C1 V1 plus C2 V2 plus dot 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 till Cn Vn, where the V matrix that I have, yeah. So, given the linear transformation A, I can always get its SVD. Once I get its SVD, I know the U matrix, I know the sigma matrix, I know the V matrix. Now, based on this V matrix that I have got, I obviously have a bunch of orthonormal vectors sitting as the columns of this V matrix, V1, V2 dot 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 till Vn, and I am saying that choose them as the basis for V, this Cn, and express this vector as a linear combination that belongs to the span of these vectors V1 through Vn, right. So, now what can I say? Therefore, Ax is equal to U, and then I have the sigma hat square root. So, hereafter I will not really write this as a sigma hat square root, this cumbersome notation, rather I would use the more explicit, more elaborate form of this notation, which is basically sigma 1, sigma 2 dot 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 till sigma r and the zeros and V Hermitian times x. But then what can I say about this V Hermitian times x? Look at this V Hermitian x. So, this is nothing but V1 star dot 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 till Vn star. This is what my V Hermitian looks like, right, times x. So, what is x? X is nothing but C1 V1 plus C2 V2 plus dot 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 till Cn Vn, right. So, this is my x. So, I am trying to get a picture of what this fellow looks like, and this fellow looks exactly. So, when I take the inner product with this fellow, it will pick out just C1, right. So, it will just pick out C1. When I take the inner product with V2 star or V2 Hermitian, it will pick out C2. Likewise, it will just pick out Cn. Just convince yourself that this is indeed so, yeah. You see, because V1 Hermitian V2 is going to be 0, because why? V is a unitary matrix, that is how the SVD works. So, now therefore, Ax turns out to be nothing but this u1, u2, now I have m, this is the U matrix, right. Now I am opening up this U, this is a Hermitian matrix or unitary matrix rather, this is a unitary matrix in m cross m of size m cross m, right. And then I have this sigma 1, sigma 2 dot 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 till sigma r, like so, and then I have the C1, C2 dot 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 till Cn. Okay. So now if I proceed to multiply them in this fashion, so let us multiply these two fellows together, what do I get? I get sigma 1 u1, sigma 2 u2 dot 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 till sigma r u r, and then I have a bunch of columns which are going to be just all zeros. It is going to be of size m cross n, right. So the remaining n minus r columns are going to be zeros. So there is going to be a column of n minus r columns of zeros. Yeah. So this obviously is of size m cross n, and then I have this C1, C2 dot 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 till Cn. So what I then end up with is basically summation Ci sigma I ui I is equal to 1 to r. So therefore Ax belongs to span of u1, u2 dot 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 till ur, which is nothing but the image of the matrix u1, u2. Remember that u hat I had described just a while back while deriving. So it is basically this u hat that matters. Okay. So therefore Ax belongs to this. So therefore I have that if anything, now where does Ax come from? Now Ax clearly belongs to the image of A. So anything that belongs to the image of A also belongs to the image of u1 through ur, right. Therefore I have that the image of A is contained in the image of u1, u2 dot 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 till ur, right. This I can now show. Conversely, can I show that if anything belongs to the image of u1 through ur, it also belongs to the image of A? Yeah, of course I can. It is exactly the line of reasoning we had followed for Hermitian matrices. You remember the result we proved in the previous lecture probably. Yeah. So let any vector say small u. So let u belong to span of, span of u1 through ur is the same as the image of u1 u to this particular matrix. This is basically u hat, the way we have defined it here. So let this belong to the span of u1, u2 dot 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 till ur. All right. Now if this is so, therefore u can be written as alpha 1 u1 plus alpha 2 u2 plus dot 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 plus alpha r ur. Now we are trying to check, does there exist P in Cn such that AP is equal to u? If the answer is a yes, then we would have shown that the span of this u1 through ur, or the image of this let us say the image of this u1 through ur is actually contained in the image of A, and therefore these two images or these two subspaces are one and the same. The way to show that one subspace is equal to another is to show that subspace 1 is contained in subspace 2 and subspace 2 is contained in subspace 1. It is containment that basically tells us that one is equal to the other. Yeah, so this question, and the answer to this question will turn out to be yes. So how are we going to prove this? Again, I am not going to go the whole way because we have already spent in a considerable amount of effort in proving something very similar for Hermitian matrices in the previous lecture, right. So you take this to be u sigma v star p is equal to, and we are trying to solve for this, right. We are trying to solve for this. So this is basically nothing but this u hat times alpha 1 alpha 2 dot 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 till alpha r. That is what we are trying to do here, right. So, now if you hit this with u star on the left, right. So, u star is of what size? Let us get the sizes right. So, this is of m cross m, yeah, and this is of size what? This is of size m cross r, alright. So, if you hit on by u star on both sides, first of all check that it is compatible for multiplication, right. So, this is sigma v star p is equal to this, you can partition as u hat star and u tilde star like this, right, and this is then u hat times alpha 1 alpha 2 till alpha r. Okay, so, this obviously pulverizes to identity. So, then you have sigma v star p is equal to, so u star u, u hat star u or u hat Hermitian u is going to lead to identity, and this latter part is going to lead to 0. So, remember the size of this is of size m cross m and this is of size m cross r. So, their overall product yeah. So, this is of size r, this is of size m, this is of size m minus r, yeah, right. So, this is of size r cross r, yeah, and this latter one, this is of size m minus r cross r, yeah. This is how this will look when you multiply these two fellows out, and then you will have alpha 1 through alpha r, yeah. So, what we are then left to show is that again if you multiply this out, you will have first these alpha r. So, this recall the size of this whole thing, yeah, this is going to be m cross r and times r cross 1. So, it is going to be m cross r, overall this thing is going to be of size m cross r, and what do we have here? This is of size m cross n, then this is of size n cross n, and this is of size n cross, sorry, this again my bad, this is r cross 1. So, this is m cross 1, this is m cross yeah, this is m cross r. So, this is of size r, this is of size m, and this is of size r cross 1. So, this is m cross 1, and on the left hand side also you have size m cross n, n cross n, n cross 1. So, it is m cross 1, yeah. So, that is the first check we do it when we calculate. Anyway, now the point is that you have this sigma 1, sigma 2 dot 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 till sigma r. So, I am now opening up everything here, all these terms here, yeah, and this is v star p, and this has purportedly got to equal, yeah, what we have here is yeah, the first r entries will be alpha 1 alpha 2 dot 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 till alpha r, and then the last few entries, this is an m cross n size, remember. So, this is m minus r size, this is going to be all zeros, right, because this 0 fellow will multiply these fellows and lead to all zeros. Now, the point is, can we solve for this? Well, we can't, we can simply confine our interest. So, how many equations are there? If we now look at it in this fashion, this part is again, now we go back to that earlier notation, this is the square root of that sigma hat, is it not? Square root of that sigma hat. So, now we can just forget about the lower half, these m minus r, because on the left hand side also you have 0, on the right hand side also you have 0. So, they are consistent. So, you basically have these r equations and there are these r unknowns that you have to find out, or rather you know this r equations, and there are these n unknowns that you have to find out in p, right, but they are consistent system of equations. So, this is a fat equation, again the same argument we made the other day, right. So, again I urge you to prove, you know, you have these row reduced echelon forms where you can show that if you have a wide matrix, yeah, if you have a wide matrix with full row rank, yeah, then a solution will always exist. Whether the solution is unique or not, that is then of concern. How to get the best possible solution in some sense, that is then the concern. But the existence of the solution is really not in doubt in such cases, right. So, again from this point I leave it to you to go and find out from a basic exercise of linear algebra, just look up row reduced echelon form and you will find out that you can always solve for this P, maybe not uniquely, but there exists some P. So, this tells us then that, well, not just that the image of A is contained in the image of U1 through UR, but the image of U1 through U2 to UR is also contained in the image of A, and therefore, the fact that the image of A is actually indeed equal to the image of U1, U2 till UR, and this is beautiful because now we know that this SVD, once you found a singular value decomposition for a matrix A in the form U sigma V Hermitian, yeah, where the sigma is basically these positive entries sitting along the diagonals till the size of the rank is met, right. Then the first R columns of the U matrix not just provide a basis for the image of A, but it also gives you an orthonormal basis for the image of A, right, and that is the beautiful result. The second beautiful result, which is sort of a dual to this, so now you apply rank nullity is applicable to any linear transformation and therefore also to matrices. So, now you apply this rank nullity result and you will then immediately be able to infer that nullity of A is equal to n minus R, and now I am claiming that the kernel of A is actually nothing but the image of V R plus 1 through till V n. First of all, notice why is this claim, why does this make sense? I mean, as in whether it is compatible with whatever we have learned so far. So, if a kernel has to have a basis, how many elements must it have? We know that the rank is R, so the kernel must have dimension n minus R, yeah. Do we have n minus R linearly independent vectors here? Of course we do, of course we do. From rank nullity, you know, these are orthonormal vectors, it is an orthonormal set of vectors, right, or rather a set of orthonormal vectors to be precise. So, when you have a set of orthonormal vectors, their linear independence is guaranteed. Because the linear independence is guaranteed, at least we know that dimensionally we are compatible. So, we do not have to really show that this containment works both ways. Once we show that one of these subspaces is contained in the other, then the dimension argument will come in handy and I do not need to show that both of them are contained in each other. I know that the dimension of the kernel is n minus R. I know that the dimension of this other subspace is also n minus R. So, two finite dimensional subspaces of equal dimension and one is contained in the other, then the other must be the same as the subspace itself, right. I mean, you cannot have two subspaces of equal dimension such that one is contained in the other and the other is not contained in the first, yeah, it is not possible, right. So, we will only show containment in one way. In other words, let V belong to, let me choose the easier route, let V belong to the image of VR plus 1 dot 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 till Vn, alright. Therefore, V is equal to beta 1 or beta R plus 1 VR plus 1 plus beta R plus 2 VR plus 2 plus so on till beta n Vn, yeah. Now, consider AV. What can we say about AV? Just look, U, then you have sigma 1 through till sigma R, yeah, and then you have, okay, let me write this down elaborately, this V, V1, V2 dot 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 till VR, and then I partition it and then I have VR plus 1 dot 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 till Vn times I have times V, which is nothing but U. So, again let me multiply these two out first, yeah, let me multiply these two out. So, what is this going to lead to? So, this is going to lead to sigma 1 u1, sigma 2 u2 dot 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 till sigma r ur, yeah, and the remaining all are going to be columns of zeros. Okay. And what about B now? This V, can I not write this as VR plus 1, VR plus 2 dot 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 till Vn, and then beta r plus 1, beta r plus 2 dot 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 till beta n, right? I can write it in this fashion. So, let me just replace it in that way. So, then I have V1, V2 dot 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 till Vr, and finally, I have Vr plus 1 dot 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 till Vn, and then I substitute for this V here. So, when I substitute for this V here, I basically get this Vr plus 1 dot 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 till Vn, and then I have beta r plus 1 dot 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 till beta n. Okay. Now, notice very carefully that each of these elements when multiplying with this V1 through Vr will lead to 0, right. Okay, let me hang on, sorry about that. Again, this has been a bit of a mess. Yeah. So, this should actually not look like this, but this should actually look like, you know, V1 star, V2 star, likewise till Vr star, Vr plus 1 star dot 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 till Vn star. Yeah, I am sorry about that, and then you have V. So, now again, let me not make that effort here, and let me just write it down, because let me be a little lazy with this. So, you know, right. Now, you look, if you multiply this Vr plus 1 with any of these first R fellows here, yeah, any of these R fellows here, it will lead to 0, undoubtedly. So, all that you have to do here is, now leave it to you as an exercise to check that this is indeed the case, sigma r ur, and then the columns of zeros, yeah. And now I leave it to you to check that only the last n minus r entries are only going to lead to something different, right, because this is a unitary matrix, this V is also a unitary matrix, all right, and I have split it, I partitioned it into r and n minus r in those two, in that manner, right. So, now what do I have remaining here? The first, well, yeah, V1 through Vr, they are all going to lead to zeros here. Yeah. So, this is going to be a row of zeros here, this is going to be a row of zeros here, and you see the first R rows are all going to be zeros. So, this is R rows are all going to be zeros, only the last R rows are going to be any different, sorry, last n minus R rows are going to be any different, yeah. So, this is of size what? This is of size n cross n, and this is of size n cross n minus r. So, this is again going to be of size n cross n minus r. This is n minus r, and this is of size n minus r, right. Just always be sure to check this, right. So, this is going to be of, yeah. So, last part is going to be of identity of size n minus r cross n minus r, and then you have this beta r plus 1 through till beta n, all right. But now, what does this mean? This means that the first r entries of this vector, of this overall vector, is going to be 0, and the last n minus r entries are going to be just this, right. So, that means this is going to be sigma 1 u1 dot 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 till sigma r ur 0 0 0 like this. And what about this? So, again recall the size of this is of size m, this is of size n, and this is again going to be of size n cross n minus r, and this is of size n minus r cross 1. So, it is going to be n cross 1, yeah. So, eventually it is going to be of size m cross 1, but what is the shape of this going to look like? So, this is 0 0 Yeah, this is all going to be all zeros. No, this row of vectors, 0 vectors multiplying with this whole thing is going to be 0. Only the last few fellows are going to be any different. So, there in the last n minus r entries I have these entries sitting from beta 1 to beta n minus r, or rather I have not named them as beta 1 through beta n minus r. So, let me maintain the nomenclature. So, this is beta r plus 1 through till beta n n. Yeah, that is what this is going to be. Yeah, all the preceding, these are how many entries? These are r entries, these are all going to be 0. Now, when you multiply this out, you see wherever there is a non-zero here, it gets multiplied with a 0 here, that column, and wherever there is a 0 column here, that is the only column that gets multiplied with a non-zero here. So, this is going to be indeed the 0 vector of size m cross 1, right. So, therefore, if you choose any vector that belongs to the image of Vr plus 1 through Vn, then it also belongs to the kernel of A. Therefore, V belongs to kernel of A, and hence the image of V1, V2 dot 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 till Vr, sorry Vr plus 1 dot 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 till Vn is contained in the kernel of A, and because it is contained in the kernel of A, and we know that the dimensions of those two subspaces are equal, therefore, since dimension of kernel of A is equal to dimension of the image of V1 Vr dot 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 till Vn, sorry, this is Vr plus 1, no, again please correct this, I am always making these mistakes in a hurry. So, please correct this is from r plus 1 through n, right. Yeah. So, then since the dimensions are one and the same and one is contained in the other, therefore, image of Vr plus 1 through till Vn is equal to kernel of A. So, not only that, the U matrix, the first r columns of U matrix give me the basis for the image, an orthonormal basis for the image of A, but the last n minus r columns of V give me a orthonormal basis for the kernel of A. So, basically singular value decomposition encapsulates within itself all the important subspaces and their basis corresponding to a linear transformation represented as a matrix, and that is the beautiful part about it. Okay. In the next class we shall discuss a few more subtle aspects of this singular value decomposition, yeah, and then we will move over to the idea of LMIs, linear matrix inequalities. Thank you.